So good evening to all of you. Today we are having the last lecture for your advanced materials chemistry course, and in this particular lecture we'll be talking about materials for heterogeneous catalysis. So what we will be covering is renewable energy and renewable fuels. Then we'll talk a little bit about the basic principles of catalysis. Then we'll talk about catalysis for the conversion of biomass derived feedstocks into fuel component. We'll also cover electrocatalyst for water electrolysis, electrocatalyst for carbon dioxide reduction, and also photocatalyst for water electrolysis. So what is basically renewable energy? So renewable energy is energy from sources that are naturally replenishing but flow limited. So renewable resources are virtually inexhaustible in duration but limited in the amount of energy that is available per unit of time. So what are the major types of renewable energy sources which you can think of? That is wind energy, there is solar energy, there's hydropower, then you have hydrogen, geothermal, ocean, and also biomass. And among the biomass, what is exactly the biomass which can actually give you this kind of renewable energy? It is wood waste, municipal solid waste, landfill gas, biogas, ethanol, biodiesel. So these are all basically things which are going to give you energy from the biomass. But why do we need renewable energy? So obviously right now you have learned so much about the environment, you know about environment conservation, you are talking about sustainability. So what exactly has been observed is in October 2023, the carbon dioxide in actually the atmosphere is around now 422 parts per million, which is almost increased by 105 parts per million in the last 70 years. So the obvious fallout of having so much amount of carbon dioxide is global warming. So global warming has kind of increased the temperature of our Earth by almost 1.1 degree centigrade in the past 200 years. Which again, if you have so much amount of these greenhouse gases in the atmosphere, it leads to ocean acidification. Then there is rising sea level because because of global warming, your entire icebergs and the polar caps, they are all melting. So you're having rising sea level of almost 3.2 millimeter each year. There is decreasing ice sheet mass. There is retreating glaciers and decreasing Arctic ice at the rate of 13% each decade. So renewable energy is crucial for mitigating this kind of climate change. Why? Because when you're using non-renewable resources, when you're using fossil fuels, the amount of greenhouse gas generation is very high. The amount of carbon dioxide is also very high. And carbon dioxide, as you know, it traps in all the IR radiations. It doesn't allow it to go back. So then what happens is your Earth is getting hotter and hotter. So that is why if you're using renewable energy, this amount of greenhouse gas emission is going to be much less, and that is going to mitigate the climate change effects, the detrimental effect of climate change. So when we talk about wind, what is the wind? You know that you are having these different kinds of windmills. So wherever there are strong winds, like in the clear hilltops particularly, turbines are being used to harness this wind energy. So turbines are placed in prevailing wind direction and they are harnessing the wind energy. The amount of power and therefore the electricity a wind turbine can produce is largely based on the wind velocity, and it is given by the equation shown over here, where power is basically equal to half of rho A V square, where your rho is nothing but your air density, which is 1 kg per meter square. Then you have A, which is the swept area, which is given by pi r square. So A is nothing but this area which is swept out by this turbine blades, as you can see. So pi r square, that is the radius which you're having. And velocity is the velocity with which it's moving. So it is around meters per second. And this power is measured in something watts. So this is how basically you are converting that wind which is moving the turbines into power, and this is the power which is generated. So obviously you can see from here the air density is something which you'll not be able to change, but what you can change is basically the area. So larger wind turbine is going to give you more power, whereas if you increase the velocity of the wind, so obviously wherever there is a higher velocity of wind, it is going to give you a lot more power because it is V to the power of Q. So this is how your wind energy is getting converted to electrical power. Then of course, solar energy, we all know thermal solar panels, they are generally used to generate the heat energy. Then photovoltaic cells, they are made from silicon, and these are used to turn sunlight directly into electricity by using this kind of concept as is shown over here. You have N-type silicon and you have P-type silicon. and you are having the sun's ray falling into it. And then what you have is basically in the semiconductor, there is movement of these charge carriers. And ultimately what you find is the sunlight is actually with the help of the semiconductor device, what you're seeing is the generation of electricity. So using this kind of solar PV cells right now, around 10.7% of the total electricity generated in India is around, that actually accounts for 36.94% of the renewable energy of India right now, the solar power. And also you have something known as geothermal. So this term itself is very self-explanatory. Geo means earth, So it is heat energy from earth. So decay of the radioactive elements and residual heat from the planetary formation, which was there like 4.5 billions ago. So that is kind of stored as the geothermal energy. So what you do is you locate these kind of areas and then you pump down water into the hot rock where this water gets heated up, and ultimately this hot water is actually giving you the steam and you're having it in the turbine, and this is the generator. And ultimately by movement of this turbine and this generator, what you are getting is the electricity, and this is being uploaded into the grid. So this is how the geothermal energy is being used. This is a renewable form of energy, of course. And one of the most oldest form of renewable energy is hydroelectric power. This harnesses the kinetic energy of running water. So water is flowing downwards with gravity, and then what happens? It spins a turbine. And of course, this is more reliable than solar and wind power, because the thing is that you are using the moving mass of the water and you are not dependent on anything else. Then hydroelectric dams, but what is the disadvantage of it? This hydroelectric dams, they are very expensive, and of course it harms a lot of wildlife, a lot of displacement of human as well as animal life is there. But definitely this is one of the most oldest and the most I would say the traditional method of harnessing of renewable energy. And around 12.3% electricity from hydroelectric schemes in India is available right now, and that is also a huge percentage of renewables in total. Then coming into another very important form of getting renewable energy is from the biomass. So this is basically renewable energy sources coming from biological materials such as plants, animals, microorganisms, and municipal waste. So when we talk of biomass, so you have what is known as these different kinds of cellulose bundles. So you can see over here, these are the cellulose bundles. So what are these made of? Please remember that biomass has three most important components. One is hemicellulose, then you have something which is known as cellulose microfibrous, and then what you have is lignin. So all these three together, they actually give you something which is known as the biomass. Okay. So from this, what are the different types of bioenergy you can get from biomass? One is the biofuels. As the name suggests, this is basically renewable energy source derived from microbial plant or animal materials. So among them, the biofuels, you can have liquid biofuels. So you can have methanol, ethanol, butanol, biodiesel, or else you can have gaseous form of biofuels like methane and hydrogen, which is generated from the biomass. Then you can have bioheat, which obviously, age old, from the caveman types, they have been burning wood to generate heat wherever there is a colder climate. Then you have also for cooking. Then you have bioelectricity, which is combustion in boiler to the turbine. And then you have something which is known as microbial fuel cells, which is basically using biomass energy to generate something which is bioelectricity. We'll talk about the microbial fuel cells in the coming few slides. So what are the different conversion processes you are having? So the different conversion processes you can have for biomass to go in to give you all these different kinds of fuels as well as electricity. One is biological conversion. Okay. So what are the different types of biological conversion? As the name suggests, so you have something which is something to do with bacteria and stuff. So you have this something known as fermentation. With the fermentation process, this biological conversion process from the biomass, you can get biofuels like methanol, ethanol, butanol. Then you have some process which is known as the anaerobic digestion. And this anaerobic digestion, as the name suggests, is you are cutting off oxygen, but then you are using it to kind of break down all the different kinds of organic material and anaerobically. And from this, what you generate is methane, which is a biogas. And then another process of biological conversion is the anaerobic respiration, which is nothing but, you are having a respiratory thing, like you are kind of burning down something like sugar, but you're not using oxygen for it. And with that, you can generate something which is known as a biobattery. Apart from the biological conversion, not only biological conversion, this is definitely one of the ways which is like more sustainable kind of conversion techniques of biomass to the different biofuels and bioelectricity. There's another type, of course, the most common one, which is the chemical conversion. So you have something which is known as transesterification of the biomass, and you can yield something which is known as biodiesel. And of course, the thermal conversion, which is nothing but heating it up using heat. So you can have combustion, you can have gasification, and you can have something which is known as pyrolysis. So these are the different techniques or the conversion processes by which you can convert the biomass to something which is more usable. So now let's look into the different biomass to bioenergy routes, a very interesting slide. So what exactly you have over here is all the different biomass. So you see the main process is given right at the top over here. So you are having photosynthesis being done by the entire plant kingdom. From there, what you have is the generation of the biomass. Then this biomass, there are various conversion processes. And from this, using different conversion processes, you're getting biofuels and bioenergy, and there is various application. So this color scheme is showing you all the different things. So photosynthesis, you know, carbon dioxide and water, it gets taken in by the plants with the help of sunlight. What you actually generate is basically C6H12O6, which is glucose plus oxygen. Now, among the different biomass, there are different types. As you can see, you can have wet biomass like organic waste and manure. You can use a conversion process like anaerobic fermentation in this case, and what you generate is biogas, hydrogen, and methane. And then you can use this biogas for various variety of things, like you can use it for generating heat, for generating electricity, and also you can process it to give you liquid biofuels. And this can have various applications in transport, in electrical devices, in heating, and ultimately it will give rise to carbon dioxide, and the cycle forms again, it again goes back to your photosynthesis. So this is the entire method. Then you have something which is known as solid biomass, like wood and straw. So with this solid biomass, you can have these various conversion processes. You can have gasification, which will give you fuel gas. You can have combustion, you can have pyrolysis, you can have hydrolysis. So you get various fuel gas, pyrolytic oil, you can also get sugar. And then from the sugar, you can get liquid biofuels, whereas from pyrolytic oil, fuel gas, you can actually get heat, electricity, and the various applications, so on and so forth. Similarly, with sugar and starch plants like sugarcane cereals, the conversion process is hydrolysis or extraction. When you generate sugar and you get ethanol, butanol by fermentation process. You have oil crops and algae like sunflower and soybean, which you can crush and refine, and you can get a lot of pure oil. And then you use this chemical conversion process like transesterification. You get methyl ester or biodiesel. And with this biodiesel, you are actually getting liquid biofuels, which can be used for transport. So this, in particular one slide, you can actually see the different biomass which can be used, the different conversion process you can use, and the kind of product you're getting and their applications. So what is the advantage of biomass? Some of these advantages, when I will read through, you'll find it's very instinctive, right? Because biomass is widespread availability in many parts of the world, right? It is available all throughout the world. And there is no such thing as, like it is concentrated only on one part and you don't get, the other parts are deprived of it, which is the case in case of fossil fuels, in case of coal, in case of oil. So you find that, some parts of the geographical parts of our universe is more rich in those kind of things, whereas the others are not so rich. So that kind of brings a kind of inequality of distribution of the geographical resources, what we have. So instead of that, in case of biomass, what you have is that there's widespread availability in many parts of the world. Then you have contribution to the security of energy supplies. Obviously, this is a fallout of that particular advantage. Then generally low fuel cost compared with fossil fuels. Biomass as a resource, it can be stored in large amounts, and bioenergy can be produced on demand. So you can store the biomass, and as and when you need it, you can produce bioenergy from it and use it. Of course, it creates a lot of stable jobs, especially in the rural areas. Then developing technologies and knowledge base, it offers opportunities for technology export when you're converting, when you're having this biomass kind of refinery. Then, of course, it is extremely good because it provides carbon dioxide mitigation and other emission reductions like that of sulfur oxides, nitrogen oxides, etc. So definitely it is very, 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 sustainability point of view, this is definitely one of the better methods. So now if we look into the environmental benefits of this, different types of this renewable energy things. So if you see, if you consider like gasoline or petroleum, you see the amount of greenhouse gas getting generated. Whereas if you are using natural gas or biomass, you just see how amount of reduction in the greenhouse gas emission. In case of natural gas, if you are producing something like corn, like maybe you are using like corn ethanol, in that case there is a 28% reduction, and in case of biomass you get a 52% reduction. Whereas if you are having biomass based, like you are having sugarcane ethanol, there is almost 78% reduction of greenhouse gas. Whereas if you are using cellulosic ethanol, you are getting from cellulose, in that case there is almost 86% reduction of greenhouse gas emissions. So these are the huge amount of environmental benefits which are provided by using biomass as a renewable energy source. But definitely there are certain drawbacks also, because you have to kind of heat up or process very high amount of biomass to get certain amount of energy, compared to the fossil fuels. You use a very less amount and you still get a very high calorific value. So that is not present in biomass, so they generally have a very low energy content. Then of course, if you are using waste, that is fine. But if you are using some food stock material, like you are using, like you are using sugars and you are using stuff like that, this becomes a competition for the resource with food, feed, and material applications like particle board or paper. That is also used. That is also kind of fabricated using biomass, right? This particle board or paper. So you are kind of this kind of generation of fuels. It definitely gives a competition to those kind of industries. And generally, there is higher investment cost for conversion into final energy in comparison with fossil alternatives. So right now, the investment costs are very high because you definitely have an option of using fossils, but tomorrow, or that means not literally tomorrow, but after a few hundreds of years, when we will definitely be starved of fossil fuels, then probably this is going to be the best way to generate energy. So what are the biofuel applications in case of liquids? So you have ethanol and butanol, which you can get from biomass, and this can be used either at low blends up to 10%, or in high blends in flexible fuel vehicles, or in pure form in adapted engines. So right now the engines which we have, you cannot use ethanol or butanol, which is obtained from biomass, directly in those engines, but you can definitely use low blends and high blends. If you want to use 100% of that, then definitely you have to change the current engines, whatever we are having. Biodiesel, it can be used both blended and with fossil diesel and in pure form. Its acceptance by the car manufacturers is gradually growing. So biodiesel definitely is finding a little more acceptance right now. So, but why butanol? Why is it that, butanol is preferred? Because when you're having something which is gasoline, compared to ethanol, butanol is more similar to gasoline. So obviously, if you're generating butanol using the biomass, it has more acceptance. So it can be transported via the existing pipelines, whereas ethanol, you cannot do it. Why you can do it using existing pipelines is because, as I said, the similarity of butanol with current gasoline. And fuel engines which are designed for use with gasoline, they can very easily use butanol without, without very drastic modifications. So the thing is that, another thing is that this biobutanol is produced from biomass, and also butanol can be produced from petroleum. So the toxicity issues, if we talk about, it is no worse than gasoline. So that's why butanol is definitely having more acceptance when it is prepared from the biomass. So how do you get the biodiesel? So biodiesel is from the triglyceride oil. So triglyceride is what? It consists of a glycerol backbone, and it has 3 fatty acid tails. Okay, there's different 3 fatty acid tails are there. So what happens is you're using either sodium hydroxide or potassium hydroxide as a catalyst. And when you're using this as a catalyst, what happens is this OH from this sodium hydroxide or potassium hydroxide, it facilitates the breaking of the bonds which is there between the fatty acids and the glycerol. Now this methanol, whatever is there, then it binds to the free end of the fatty acids, and it produce a methyl ester, as you can see over here. So what you have over here is right now a methyl ester. And this is nothing but biodiesel. So this particular thing is your biodiesel, and this is how you get it using triglycerides. So, but you have to remember that it is a multi-step reaction mechanism. So from the triglyceride, we move to diglyceride, then we move to monoglyceride, followed by formation of methyl esters and glycerin. So this is how you generate biodiesel from the different triglyceride oils. So what are the biofuel application in case of gases? We spoke about the liquids. In case of gases, hydrogen, of course, can be used in fuel cells for generation of electricity. Methane can be combusted directly or it can be converted to ethane. So these are all the different applications. Then bioheat, as I said, you can use it directly for small scale heating system for households, typically using firewood or pellets. Medium scale, you can use burn wood chips in the great boilers, and then you can, kind of have a lot of heat generated. And that kind of heat is normally used for heating up a house, a small house kind of thing, or maybe a small building. Then large-scale boilers, they are able to burn a large variety of fuels, including wood waste and refuse-derived fuel, and that you can use for generating heat for or thermally insulating very big buildings. What are the applications of bioelectricity? So this is generally cogeneration. You have a combustion which is followed by a water vapor cycle driven turbine engine, and which is the main technology right now which is being used. And the other way of generating bioelectricity is obviously microbial fuel cells, which is direct conversion of the biomass to electricity. Whereas in case of cogeneration, what is happening? First you do a combustion, then you have a particular water vapor cycle, the normal water vapor cycle. The vapor is generated, the steam is generated, it is driving a turbine engine, and then you are having the electricity generation. So that is a kind of cogeneration. Whereas with MFCs, what you do is directly you are converting the biomass to electricity. So how do you do it? So you have this entire cycle over here with this glucose and with this bacteria working over here. So you have an anode and you also have a cathode, and you have a proton exchange membrane over here. So the electrons are flowing from an anode through a resistor, as you can see over here, to a cathode where electron acceptors are reduced, and the proton flows across the proton exchange membrane and it completes this entire circuit. So this is how you have the microbial fuel cell. So you have this entire biomass over here on this side with the anode, and then with the cathode, what you're having is a proton exchange membrane. And then protons will flow across this proton exchange membrane and it completes the circuit, and this is how your electricity is generated. So you can have two compartment microbial fuel cells. So one is, and then you have a proton exchange membrane which can be Nafion or Ultrex. The electrodes are generally graphite plates. The working volume is around 400 ml. So these are the microbial fuel cells which you generally find in the lab. So you can have this kind of anode. You can see the biomass over here in the anode, and then you have the cathode, and this is how the electricity is getting generated with the MFCs. One of the very important point, as I said, is we are talking about heterogeneous catalysis and also homogeneous catalysis, which we'll cover. So why we are talking so much about this kind of this renewable energy and biomass thing is that you need some catalytic converters, So you need catalytic conversion of biomass derived feedstock to the renewable fuels and chemicals. So for catalytic conversion, because it makes the process less energy intensive. Okay, when you're using a catalyst, it makes the process less energy intensive. It kind of brings down the cost. It brings down the running cost of that entire process. So what we need to do is design more active, selective, and stable catalysts. And you need to elucidate a more detailed understanding of the catalytic chemistry which is underlying these processes. So biomass to biofuel generation, so the catalyst you kind of use, you need to have a little more understanding of these different chemistries which are working. So what is catalyst? We all know, we have read it since our high school level, that catalyst is an action by catalyst which takes part in chemical reaction process, and it alters the rate of the reaction. But it itself will return to its original form without being consumed or destroyed at the end of the reaction. So you have something which is an uncatalyzed reaction. So you have reactants, you have the products over here. You see the relative energy of these reactants and the products. And what happens is you have something which is known as this activation energy. So normal process without the catalyst, this is the activation energy. As you can see over here, this is much higher. The moment you're putting in a catalyst, this activation energy is coming down, as you can see over here. And this particular energy is much less compared to what it would have been if the reaction was uncatalyzed. So this kind of gives you an idea that what catalysis is actually doing. So now there are three aspects of this catalyst action. One is you take part in the reaction, the catalyst will take part in the reaction. So it will change itself during the process by interacting with other reactant products or molecules. Then it will alter the rate of reaction. In most cases, the rate of reactions, they are increased by the action of catalyst. However, in some situations, you will find that the rate of undesired reactions are also selectively suppressed. So that is also, when such a thing happens, that is also a catalyst. Then, of course, the catalyst will return to its original form. So after reaction cycles, a catalyst with exactly the same nature is kind of reborn. So in practice, please remember, catalyst has its lifespan. It deactivates gradually during use. So normally we have read this, catalysts, it just goes on and on and on. It doesn't work that way. It also has a lifespan. It also has a time till the time its efficiency is really high and you use it. With prolonged use, what happens? The efficiency gradually falls off. So that is a practical situation. Whereas ideally, if you think the catalyst should actually continuously, alter the rate of the reaction of the process and it should come back to its original form. But practically, it doesn't happen that way. So catalysis action is what? It is reaction kinetics and mechanism. So catalyst action, it leads to a change in the rate of the reaction. As I said over there, that it basically brings down the activation energy. So this is realized by changing the course of reaction compared to the non-catalytic reaction. So it forms a complex with the reactants products, controlling the rate of elementary steps in the process. And this is evidenced by the fact that the reaction activation energy is altered, as I said. The intermediates formed, these are different from those in the non-catalytic reaction, and the rates of reaction are altered, both the desired as well as the undesired ones. And the reaction then proceeds under less demanding conditions. Only then it is a good catalyst. Okay, the reaction, whatever reaction for which you have designed that catalyst, that reaction should proceed under less demanding conditions. And you allow the reactions occur under a milder condition, for example, at lower temperature for different heat sensitive materials. So now you have to remember one thing, that use of catalyst, it does not vary the delta G or the K equivalent values of the reaction. So it mainly changes the pace of the process. So whether a reaction can proceed or not, or to what extent this reaction can proceed, is solely determined by the reaction thermodynamics, which is governed by the values of delta G and K equilibrium and not by the presence of the catalyst. In other words, what is this? The reaction thermodynamics, it provides the driving force for a reaction. The presence of catalyst changes the way how the driving force acts on that process. So this is a very important thing. Okay, so this is basically how driving force actually acts on that particular process. So now suppose you have this particular reaction where methane is reacting with carbon dioxide, giving you carbon monoxide and hydrogen. Look at the delta G values at different temperatures. At 100 degrees centigrade, it is plus 151 kilojoules per mole. Then obviously, this particular reaction is non-spontaneous because delta G value is positive. Whereas if you are bringing up the temperature to 700 degrees centigrade, then the delta G value becomes minus 16 kilojoules per mole. So then the process gets spontaneous. So when you're doing this reaction 100 degrees centigrade, when the delta G value is positive, so there will be no thermodynamic driving force and the reaction won't proceed, whether you use a catalyst or you don't use a catalyst. But when it is at 700 degrees centigrade, this delta G value is negative. So the thermodynamic driving force is there. But if you simply put methane and carbon dioxide together in a reactor, it doesn't mean that it is going to react. So without a proper catalyst heating the mixture in reactor, results no conversion of this methane and carbon dioxide at all. So when you are having this catalyst like platinum on zirconia or nickel on alumina, which is present in the reactor at the same temperature, equilibrium conversion can be achieved, which is of course not 100%, less than 100%. So please understand this thing, that catalyst will not vary delta G and K equilibrium value, but it will merely change the pace of the reaction. So now there are 5 broad classes of catalysis research. One is biocatalysts, which are the different enzymes, and this is used for water oxidation and photosynthesis. Then you have homogeneous catalysis, which are different transition metal complexes, and they are generally used to give you to synthesize fine chemicals and olefin metathesis. Then you have something which is known as electrocatalysts, which are platinum nanoparticles, which you will read a lot in fuel cells and water electrolysis. Then you have conventional heterogeneous catalysis, which are mostly rhodium nanoparticles, and they are found in catalytic converters in ammonia synthesis. And then you have ultra high vacuum surface science, for which ruthenium is very, very important. And these are used for various kind of fundamental studies, adsorption, desorption, reaction. So these are the 5 broad classes of catalysis research. Okay. So what are the solid catalysts? So, when you're talking about solid catalysts, they have the composition is, it's having an active phase, it is having a promoter, and it is also having a support or a carrier. So what is the active phase? This is basically where the reaction occurs. So this is basically the main, or you can say the heart and lungs of your catalyst. Okay, so it is mostly metal or metal oxide. Then you have a promoter, which is nothing but it can be a textual promoter. Like you can have aluminium ion for nitrogen, aluminium and ion for nitrogen, for ammonia production. It can be an electric or structural modifier. It can be a poison resistant promoter. So having that promotes the catalytic activity. It is not that it itself is acting as a catalyst, but it promotes the activity of the active phase of the catalyst material. And then of course you have something which is known as support or carrier, which is used to increase the mechanical strength, to increase the surface area, because catalyst, is a surface activity. More the area, the more amount of reaction becomes feasible. So the support or carrier, you can either have a catalytically active material or you can have a catalytically inactive material. So this is basically the composition of a solid catalyst. What are some common solid support or carrier materials? It can be alumina, which is inexpensive and it's acidic in nature. Then you can have silica, which is also inexpensive and acidic in nature. And you can also have zeolite, which is a mixture of alumina and silica, and often exchanged metal ion present. It is shape selective and it is also acidic. There can be other supports also. You can have active carbon, you can have titania, you can have zirconia, you can have magnesia, you can have lanthania. So all these supports, they have different kinds of surface area, and these all can be used as a common solid support or carrier material for your active catalysts. Okay. So how do you prepare it? So there are certain techniques. You use it doing precipitation techniques. Then you can have adsorption and ion exchange. Then you can impregnate it. That is, you can do an impregnation step where you fill the pores of support with a metal salt solution of sufficient concentration to give it a correct loading of the catalyst material. Or else you can also have a dry mixing, which is physically mixed, then grounded and fired. So these are the different methods in which you can actually get your solid catalysts. Then this catalyst, whatever you got by using these above methods, it has to be calcined or fired in order to decompose the precursor and to acquire desired thermal stability. The effects of calcination, temperature and time, these are shown over here. How you see the surface area. If you are increasing the temperature, the surface area decreases. And if you are increasing the time for which this entire thing goes on, then also you will find that the surface area decreases and kind of reaches a plateau. So what is a typical catalyst lifespan? It can be many years or it can also be few minutes. So if you see the activity versus time, normally it looks like this. You have an induction period, then you have normal use period, and then of course the activity falls down and it becomes a dead catalyst. Okay. So why is catalysis considered as a green chemistry? Because it makes the entire process less energy intensive. It uses the stoichiometric amount of reagents you can use. Then it also reduces the formation of byproducts, particularly if the catalyst is highly selective, and it also reduces generation of waste. So if you recall the principles of green chemistry, you must remember that it is better to prevent waste than to treat or clean up waste after it is formed. Then energy requirements should be minimized. Synthetic methods should be conducted at ambient temperature and pressure, and catalytic reagents are superior to the stoichiometric ones. So that's why catalysis is considered to be a green chemistry. But there are certain disadvantages also of catalyst, because some problems are that the separation of the catalyst residue from the finally wanted product sometimes becomes an issue. Recycling of the catalyst sometimes can really give you a lot of pain. Then degradation of the catalyst can happen. Toxicity of the catalyst is also very important. One particular reaction, whatever it is catalyzing, it might be that, along with it, it's catalyzing a particular reaction, but the catalyst itself is toxic. So you can have catalyst which is toxic, you can have catalyst residue which are toxic, or you can have catalyst degradation products which are toxic. But however, even in spite of all these disadvantages, they are very minor points. But in general, you have to understand that it is greener to use catalysts than to not use them. And that is why I have highlighted this particular point over here. So let's look into how catalyst helps. A few examples. So now ibuprofen. Ibuprofen is such an important anti-inflammatory drug, and it's used as a painkiller. And so the synthesis, if you see, it starts from this particular compound, and what ibuprofen is particularly this compound. So you see the number of steps which are involved. So there's 1, 2, 3, 4, 5, 6 steps. This process synthesis of ibuprofen. This is a normal process, but you can also synthesize the same thing using only 3 steps, and you can have catalyst for each step. Like you can have hydrogen nickel catalyst for transforming this particular ketone to the alcohol and then to the CO2H group. So to form this ibuprofen, you can use the hydrogen nickel catalyst, and then you can follow it up by palladium and carbon monoxide. And using this, what you find is there is 99% conversion, and the selectivity is also very high. It's 96% selectivity, and very less waste is generated. So definitely it is a winner, this particular thing. So now catalysis, there are of 2 types. You can have a homogeneous catalysis, you can have heterogeneous catalysis. So what is homogeneous catalysis? In this case, as the name suggests, reagents and the catalyst, they are all in the same phase. So typically they are all in solution. The other method is basically heterogeneous catalysis, or which is surface catalysis. So reagents, these are now in a different phase compared to the catalyst. So usually the reagents are gases or liquids and are passed over a solid catalyst. Example, catalytic converters in car exhaust. And another very important definition you have for catalysis is biocatalysis, where you are using enzymes to catalyze a particular reaction. So what are the advantages and disadvantages of heterogeneous catalysis and homogeneous catalysis? So if you look into the advantages of heterogeneous catalysis, it is readily separated, it is readily recycled or regenerated, it is long-lived, and it is cheap. Whereas if you look into the homogeneous catalysis, the advantage it has very high rates, it is robust to poisons, it is highly selective, it has very mild condition in which it works, and the mechanism is often known. But there are many drawbacks also of heterogeneous catalysis. One is the lower rates, which is diffusion related, diffusion limited. Then you have generally a high energy process. You have poor mechanistic understanding. You have lower selectivity. Whereas in case of homogeneous catalysis, the disadvantages are it is very difficult to separate, it is difficult to recover, it has a very short service life, and it's also sometimes pretty expensive. So ultimate goal is what? You have to combine the fast rates and high selectivities of homogeneous catalysts with the ease of recovery or recycle of the heterogeneous catalyst. So this forms the crux of all research which is being done in catalysts right now. So what are the applications? Used in refining. So this heterogeneous catalysis is used in refining, bulk chemical synthesis, used in refining many things in bulk chemical synthesis, which is much more than in fine chemicals and pharmaceuticals. For production of fine chemicals and pharmaceuticals, mostly you use homogeneous catalysis, whereas for refining and bulk chemical synthesis, what you use is heterogeneous catalysis. So you have to understand what are the different stages of surface catalysis. First is diffusion of the substrate towards the surface. This is followed by physisorption. So that is physical absorption via weak interaction. So you have these van der Waals forces acting with each other, and it adheres your substrate to the surface. Then you have, chemisorption. So there is a formation of chemical bonds between the surface and the substrate. Then you have migration of the bound substrates to the active catalytic sites, which is also known as surface diffusion. So it just migrates and it diffuses towards the active catalyst sites. Then the reaction happens. After this, the product is formed. There is resorption of the products from the surface, and then it diffuses away from the surface. So these are basically the 7 stages of surface catalysis. So normally for heterogeneous catalysis, what you have is a metal or a metal oxide, which is impregnated onto a support, which is typically silica or aluminum. And this 3-dimensional highly porous structure they have with a very high surface area. So what happens, as you can see, you have these reactants A, B, and C. The diffusion diffuses itself to the surface. There is physisorption, then there is chemisorption, then there is surface diffusion and reaction, and ultimately what you have is AC and BC, which are the products which are formed, and there is desorption and diffusion out of the pore. So this entire process takes place in the porous support. So you have to understand that approximately 130 industrial processes, they use solid acid-base catalysts. And these are mainly found in bulk petrochemicals production, example, dehydration, condensation, alkylation, esterification. So all these different processes, they use different kinds of catalysts. Most of this, you have to remember, are acid catalyzed processes. Then approximately 180 different catalysts are employed. For industrial process, I said around 130, which use solid acid-base catalysts. But apart from the acid-base catalysts, also you have approximately 180 different kinds of catalysts employed. Among them, you have 74 of them which are like zeolites, where ZSM is 5 is the largest group. And second largest group are, of course, the different oxides of aluminium, silicon, titanium, and zirconium. So what are zeolites? As I discussed in one of the previous slides, these are crystalline inorganic polymer which comprises of silica and alumina tetrahedra, formerly derived from silicon hydroxide and aluminum hydroxide with metal ions balancing the negative charge. So this lattice, it consists of interconnected cage-like structure, as you can see over here, featuring a mixture of pore channel sizes depending upon the aluminium silicon ratio. So this pore size you can kind of alter or design by changing the aluminium to silicon ratio, and you employ a counter cation at the level of hydration, synthetic conditions. If you just keep on tuning them, you can actually design your zeolite. So the hydrated nature of zeolites allows them to behave as Bronsted acids. Okay, so if you look into ZSM5, it has channels cross in three-dimensional, so it is a very highly porous material. And this is how it generally looks. The top view and the side view looks somewhat like this. So in a, like, you have traditional synthesis when you are synthesizing cyclohexanol, what you are doing is you are having this benzene, and to it you are using hydrogen nickel, then followed by for adding in some cobalt and oxygen. And what you see is that you get the formation of both the hydroxide as well as a ketone. Okay, so you get cyclohexanol as well as you get this ketone formation. So for selectivity reasons, this reaction is run at low conversions, approximately 6% per tank, and the hot cyclohexane stream is continuously recycled. So obviously it becomes a very messy process and expensive process, right? Because the temperature which you need is 225 degrees centigrade. You need a pressure of 10 atmospheres. And then like the yield is also very low, only 6% per tank. So obviously what better you can do? So you can have a zeolite catalyzed process. So where you are using hydrogen and nickel to convert this benzene to your cyclohexene. And then you can have this ZSM5 catalyst at only 100 degrees centigrade. It reacts in the presence of moisture or water, and what you get is a cyclohexanol. And in this case, the selectivity is around 98%. So you can see the phenomenal change and the phenomenal improvement in reaction yield as well as the general process which happens when you're adding a catalyst. Then zeolites can also be used for shape selective alkylation of toluene. So you have toluene, you're adding methanol, and then you're using this ZSM5 catalyst. So this channel size, it only allows the paraxylene to emerge, and only paraxylene is required for your PET synthesis. And so this polyethylene terephthalate synthesis, this particular JSM5 forms a very, very important catalyst. Okay, so this is the kind of application you have for zeolites. Then you can also have a rare example of solid base catalysis. So traditional synthesis of 5-ethylene 2-norborane, which is ENB, commonly known as via VNB, is vinyl norborane. So this is how the entire process looks. The base used for this isomerization is typically sodium-potassium alloy and liquid ammonia. The advantages are that ammonia is easily recycled, but the metal recycle becomes very difficult, and sodium and potassium is very dangerous, much more reactive than either sodium or potassium. So you have to understand, as such, sodium or potassium is extremely reactive, but the sodium potassium alloy is further more reactive than that. So what you can do is, basically, this is what the scientist Sumitomo he proposed, and since then this process is known as the Sumitomo process. So the base is a heterogeneous catalyst which is composed of sodium and sodium hydroxide and alumina. It has a very high reactivity. The isomerization, it proceeds at room temperature. The catalyst is readily recycled, and the catalyst which is used is much safer than the sodium potassium alloy which we were using earlier. So definitely the solid base catalysis, this is one of the very good examples. So now catalytic biomass conversion. So this we were talking about normal compounds, one compound you have, you're synthesizing another compound from it. But when we talk into biomass, this particular challenge becomes manifold. Why? Because biomass is a complex and diverse feedstock. It composed of a variety of oxygenated polymers, minerals, and extractives. And this lignocellulosic biomass is a solid non-volatile material that contains up to 50% weight percent of oxygen. And this must be removed via chemical transformations to afford higher value products or fuels that are compatible with current infrastructure. And also the minerals in biomass can be present in amounts excess of 20 weight percent. And then there are strategies which will be needed, to utilize or remove them during the biogas upgrading. So components present in biomass, what happens is can catalyze homogeneous side reactions, altering yields and selectivity as compared to the reaction of isolated, well-defined model compounds. So example is like when you're hydrotreating the pyrolysis oils, organic acids present in the oil can catalyze the enolization of hydroxyacetone. The rate of hydrogenating a carbon-carbon double bond is often faster than the rate of hydrogenating a ketone, which in part explains the product distribution resulting from this particular process. So you have to understand the components present in the biomass itself can catalyze some homogeneous side reactions. Then also components present in the biomass can inhibit desired reactions by strongly binding to active sites. So for example, minerals in the biomass, it can poison the zeolite catalyst. And similarly, organic acids in pyrolysis oil can inhibit the hydrogenation ability of the common catalyst. So these are the problems associated with it. Then realistic biomass feedstocks often contain species that are present as structural and or stereoisomers. So when glucose dissolves in water, it gives you 5 different equilibrated isomers or tautomers whose speciation depends on factors such as solvent composition and reaction temperature. So this speciation, it affects the reactivity. Like fructose is more readily dehydrated to 5-hydroxymethyl furfural than the pyranose form or glucose. And as such, the conditions under which fructose is predominantly the furanose form leads to a higher HMF, that is hexamethyl furfural selectivity. Thus, the presence of a Lewis acid catalyst, which facilitates the interconversion of these two isomers, can improve the yield of this hexamethyl furfural from glucose. Okay. So what is the possible scheme if you want to have a chemocatalytic biorefinery? You have this lignocellulose material. You can separate out the lignin. You can do chemical conversion of the lignin to give you phenols, aromatics, dibasic acids, and olefins. Or else you can have catalytic hydrolysis and depolymerization of the lignocellulose, and you can get cellulose and hemicellulose. You can do a catalytic refining over it, and you can get biofuels. Or else hemicellulose and hemicellulose, you can do dehydration, and you can get furfurals, which is biofuel, and chemicals. You can do aqueous phase reforming, by which you can get hydrocarbon and biohydrogen. Or else you can do a fermentation process and can lead to the formation of various alcohols like biofuel and chemicals. So if you look into petroleum versus biomass processing, how is it? So you have petroleum, you have a fractional distillation, you have these different hydrocarbons coming in, you adjust the molecular weight and the structure, and then you get the gasoline, diesel, or jet fuel. Or else you can have these oxygen additive steps, and you can lead to the formation of various chemicals. Whereas in case of biomass, you pre-treat by doing hydrolysis processing, and you get all these different platform molecules. Then you do the molecular adjustment like aldol condensation, ketonization, oligomerization. Or else you can also have a dehydration, hydrogenation, decarbon or decarboxylation, carbon monoxide hydrogenolysis, all these different steps, and you can yield in getting gasoline or diesel or jet fuel. And you can have various of these platform molecules throughout this hydrolysis processing. And from those platform molecules, you can generate chemicals. So this is in a nutshell, the petroleum processing and also the biomass processing. So what are the common reactions which are involved in the biomass process? One is dehydration, second is hydrogenation, then third is hydrodeoxygenation. So if you have C5 oligomers which you need to transfer into furfural, so this is basically the process you will be doing. You will add in water, there will be a hydrolysis, you will get the formation of xylose, and then you can dehydrate it, and what you get is furfural. And you can use this particular thing when you are having the C5 oligomers and you're doing a hydrolysis. You can have these various catalysts, the catalysts which are listed over here. Please remember, all of them are having boron trifluoride or boron tetrafluoride, as well as they're also having something which is known as sulfonic acid present in them. Okay. Then you can also have CC coupling reactions. Ketonization processes involve condensation of 2-carboxylic acid molecules to produce a very large 2n-1 symmetric ketone. This reaction possesses great potential for the catalytic upgrading of biomass, since CC coupling takes place with simultaneous oxygen removal from carboxylic acids, the latter of which are common intermediates in biomass conversion processes. And this reaction is typically catalyzed by inorganic oxides such as ceria, titania, alumina, zirconia at moderate temperatures around 573 to 698 Kelvin. So form and technology utilization perspectives of alternative fuels is, if you have different types of fuels like biofuels, alcohol-derived fuels, pyrolytical oil, so you use them in the liquid form, you use them in IC engines, and the application is in heavy-duty vehicles, in shipping, in industrial applications. Similarly, the liquid you can use in gas, steam, and turbine, and you can use it in steam generators, gas turbines, industrial application, aviation. And also this biomass non-recyclable waste, you can use it in the solid form. Again, you are kind of burning it in the gas or steam turbine, and you have all these other applications. Then you can have different other fuels like hydrogen, ammonia, syngas, biogas, all generated from biomass, and you can use it in the gaseous form in the fuel cell, and you can use it for transport. You can also use to power the different plants. So if you look into the evolution of fuels in terms of hydrogen to carbon ratio, what you find is that more and more hydrogen is there in the material when you move from wood to coal to oil to gas, whereas hydrogen is of course made up only of hydrogen. So the power package for the future, how it is going to look. So you will have you generally have a lot of water, so you can use an electrolyzer and you can generate oxygen, and the hydrogen you can use for hydrogen storage. This hydrogen you feed into your fuel cell, and you also have that water, which is that oxygen which is generated coming into the fuel cell. So you have water coming out and you have electric power. So ultimately, using an electrolyzer, hydrogen storage, and fuel cell, that is the ideal combination. You go from water to water, and what you have is nothing but power, generation of electrical power. So this is going to be the solving the aim in which different scientists all over the world globally are working together to realize this dream. So what is an electrocatalyst? So electrocatalysis may be defined as the relative ability of different substances when used as electrode surfaces under the same condition to accelerate a given electrochemical process. Okay, so this is what an electrocatalyst is. So why do you need electrocatalyst? So one of the main things, as I said, for electrolyzer is to electrolyze water. So generally, the overall reaction of water electrolysis is divided into two half-cell reactions. So you have HER, which is the hydrogen evolution reaction, and you have OER, which is the oxygen evolution reaction. So if you look into the hydrogen evolution reaction, the thing you have is basically where water is reduced at the cathode to produce hydrogen, as you can see over here. And oxygen evolution reaction is the reaction where water is oxidized at the anode to produce oxygen. So now what is the delta G value for this particular reaction, where your E value is electrode potential is around minus 1.23 volts, whereas the delta G value is 237 kilojoules per mole. So now you have to understand that one of the critical barriers that keep water splitting from being of practical use is the sluggish reaction kinetics. So the sluggish reaction kinetics is the most important obstacle in this oxygen evolution reaction and hydrogen evolution reactions, and this rises due to the very high overpotential in this reaction. And this overpotential is nothing but a measure of the kinetic energy barriers. So that is why, as I said, catalyst helps in getting down that particular energy. It works by altering the path by which you can have, less kinetic energy. So it brings down the kinetic energy barrier or the activation energy. So that is why catalysis plays a major role in oxygen evolution reaction as well as with hydrogen evolution reaction. So if you look into it, this electrolytic water splitting is not only an uphill reaction as reflected by the positive value of delta G, but also has to overcome a significant kinetic barrier. So catalyst will play a crucial role in lowering the kinetic barrier, as you can see. So water electrolysis, it requires a higher potential than the thermodynamic potential, which is 1.23 volts, to overcome the kinetic barrier. And this excess potential is known as overpotential. If you remember in previous slides, I have already explained to you when I first started with electrochemical process, I have explained that entire overpotential thing. So this mainly comes from that intrinsic activation barriers present on both the anode and the cathode. So usually the overpotential value corresponding to the current density of 10 milliampere per centimeter square is used to compare the activities among the different catalysts. So there is very important concept over here. One is Staffel slope and other is the exchange current whenever you're talking about catalysis. To assess the activity from the overpotential versus kinetic current relationship, this is particularly this equation. So eta is equal to A plus B log J, where eta is the overpotential and J is the current density. Now this B is nothing but the Staffel slope. This is related to the catalytic reaction mechanism in terms of the electron transfer kinetics. So if there is a smaller Staffel slope, it means that there is a significant current density increment as a function of the overpotential change. Or in other words, you have a faster electrocatalytic reaction kinetics. And the exchange current density, which is this J, it describes the intrinsic charge transfer under equilibrium conditions. So a higher exchange current density means a greater charge transfer rate and a lower reaction barrier. So obviously from this particular equation and from this explanation, you can see that a lower Tafel slope and a higher exchange current density is what it's going to denote an electrocatalyst as a better electrocatalyst, okay? So the longer the tested current or potential remains constant, if you see over here versus time, the better is the stability of this electrocatalyst. So now this turnover frequency is a very important number for any catalyst. So turnover frequency describes how many reactants can be converted to the desired product per catalytic site per unit time. So the definition of Faradaic efficiency is the ratio of experimentally detected quantity of hydrogen or oxygen to the theoretically calculated quantity of hydrogen or oxygen. And these theoretical values can be calculated from the integration of the chronoamperometric or chronopotentiometric analysis. And the experimental values are measured by analyzing the gas production using the water gas displacement method or gas chromatography method. So this is how you evaluate the performance index for the electrocatalyst. So what are the different reaction steps in hydrogen evolution reaction? So you can have one kind of step in the acidic medium and the other kind of step in alkaline medium. So acidic medium steps are shown over here where you are actually having this proton, that is why it's an acidic medium, and you generate hydrogen. Whereas in alkaline medium, what you have is this OH minus, and this is actually going to help you getting this generation of the hydrogen. Now, if you look into the volcano plots, these are nothing but these different materials which can be used as catalysts. What you have is this exchange current density, what you have on the y-axis versus the MH bond energy. So this metal hydrogen bond energy versus the exchange current density, if you plot, you see this kind of a volcano, and right at the top what you have is the highest exchange current density, and whenever it is highest, you know that it is the best electrocatalyst. So you can see for all this HER based this acid in the acidic medium, basically platinum, if you look into it, platinum is having the best kind of, it is the best catalyst for this kind of hydrogen evolution reaction in the acidic medium. Whereas if you are having monometallic surfaces, exchange current density on monometallic surfaces, then in that case, if you are having this calculated, the value for an alkaline medium, here also if you look into the different catalysts and the volcano plot, the highest exchange current density is coming again for platinum. So whether you use platinum in an acidic medium or an alkaline medium, platinum as catalyst is going to give you the best kind of activity when you see for hydrogen evolution reaction. So now, but platinum, the problem is that it is a noble metal based electrocatalyst, very costly. So what we need is non-noble based metal based electrocatalyst. So so we are having this different strategies being developed to have better electrocatalyst for her. So for the noble metal based electrocatalyst, especially the platinum based catalyst, several strategies are being developed to increase the hydrogen evolution reaction performance and lower the electrocatalyst price. So one thing you can do is you alloy the platinum with other low cost transition metal, and this improves the platinum utilization, and it can have a synergistic effect of alloy which modifies the electronic environments to improve the activity, catalytic activity. You can also couple platinum with other water dissociation promoters, since it's an important strategy to improve the alkaline hydrogen evolution reaction activities, which is very meaningful for industry practical use. In case of the non-noble metal-based hydrogen evolution reaction catalyst, electrocatalyst, so a lot of attention has been drawn to their development, largely based on the considerations of the low cost and earth abundant characteristics. So you have various of this earth abundant materials being used and their electrocatalytic activity being tested. So this forms a large part of the catalysis research. Then coming to the different reaction steps in oxygen evolution reaction. So you can have an adsorbate evolution mechanism, or you can have it in the alkaline medium. So this reaction, this oxygen evolution reaction, it occurs at the anode, and it is a 4-electron transfer process. So it has to overcome a remarkably high overpotential compared to hydrogen evolution reaction. So that is why, though for hydrogen evolution reaction you have a lot of electrocatalysts, it is more important to design good electrocatalysts for the oxygen evolution reaction. And over here, if you look into the volcano plot as shown over here, you will find that ruthenium oxide definitely is one of the best electrocatalysts if you have for oxygen evolution reaction. Then you also have something which is known as carbon dioxide reduction, electrocatalytic carbon dioxide reaction. So what is this? You are producing an anthropogenic carbon cycle by converting the carbon dioxide and water into fuels and chemicals using solar or other form of renewable energy, which is an appealing strategy to remove excess carbon dioxide. So you are already having a lot of carbon dioxide being generated, which is a greenhouse gas, and it is giving rise to the greenhouse effect. So if you can kind of, use that carbon dioxide and convert it into fuels and chemicals, in that case, it is going to be a very effective use of carbon dioxide. So what you exactly are doing is from the fuels and chemicals, you are consuming it, you are having a lot of carbon dioxide emission, and then you are doing carbon dioxide capture and purification. You have this purified carbon dioxide stored in cylinders, and then you're reducing this to give you, various usable fuels and chemicals with the help of renewable energy. And so this becomes a kind of a closed cycle. So this is also a very hot area of research in case of electrocatalysis. So these are the various carbon dioxide reduction reaction, half reactions, what you see over here, generating different kinds of products. You can have carbon monoxide generation, you can have formic acid generation, you can have methanol, you can have methane, you can also have ethylene, you can have ethanol generation. So these are all these different kinds of products you can have from carbon dioxide reduction. But you have to remember the major problematic step for this electrocatalytic carbon dioxide reduction is that the activation energy of the carbon dioxide molecule to form the CO2 dot minus radical anion. This is the first elementary electron transfer step in carbon dioxide reduction reaction, and this proceeds at a very negative applied potential, around minus 1.9 volts versus standard hydrogen electrode at a non-catalytic surface. So that is why in the development of electrocatalysis for this carbon dioxide reduction reaction, it is vital to lower the kinetic energy barriers and improve energy efficiency. So the first step itself is such a energy intensive step that it becomes very difficult to get these kind of carbon dioxide reduction reaction happening. So you have to understand this carbon dioxide reduction reaction is a complicated multi-electron and multi-proton transfer process. So proposing a definitive mechanism for a given reaction is very challenging. So there are almost 16 products which include a wide range of alkanes, alkenes, aldehydes, ketones, alcohols, carboxylic acids, which has been identified when you are using a copper catalyst for this carbon dioxide reduction reaction. So you can see there's various kinds of possible C1 pathway, C2 pathway, C3 pathway, which are happening when you're having a copper surface and solution. Okay. So these are the different, it's a very complicated multi-electron and multi-proton transfer process, as you can see over here. So catalyst design strategies are very important in this case. So what are these different design strategies? So one is that either you increase the current density or you lower the overpotential. So these are the two ways you can actually have a very good catalyst. And of course, selectivity also plays a very important role, how selective your catalyst is. So what are the different strategies? So you can have something for the current density, you have to play with the catalytic site density. So when you're talking about the site density, in that case, the major thing becomes the geometric structure. And the geometric structure you can do by, playing around with your synthesis process. So you can have dendrite structure, you can have porous, you can have rough surface, you can have confinement, you can have a 3D substrate, you can have size reduction. So all this will change your geometric structure, which is going to change the catalytic site density. Of course, your intention is to improve the catalytic site density so that the current density is improved. And this catalytic site density will also have an indirect role to play on the selectivity as well as on the overpotential. And now if you look into lowering of overpotential, then you have to lower the intermediate binding energies, right? So that means you have to play around with the electronic structure. So how do you play around with it? So you generate vacancy in your particular material. You can do alloying. You can use single atom. You can do different heterophasic junctions. You can put in some attach in some surface groups. You can do a coating. You can do doping. So all these things are going to change your electronic structure. And that will change the intermediate binding energy, which has a direct effect on the overpotential. It also has a direct effect on the selectivity, a tenacious combination with the current density. So ideally, what you need to do is you need to balance all these three. And with that, so basically you can have a grain boundary thing, you can have step and terrace, you can have exposed specific facets or site quantum confinement. So they play a role, in both of this. So it increases the over potential, it increases the current density. So all these different kinds of, synthesis strategies and using different materials, combination of different materials, you can actually design catalysts which can be used for carbon dioxide reduction reaction. And this forms a very huge part of current level of research which is going in electrocatalysts. So here I have given you one slide. You need not, go through all this, the three reaction pathway for carbon dioxide reduction, which actually gives rise to gives the product as formic acid, using different electrocatalysts. What thing I want you to see is that when you are again using, these different materials as catalysts over here, you find that tin forms one of the best electrocatalysts for carbon dioxide reduction to give you formic acid. So all these tin-based compounds, they definitely give you, they act as good electrocatalysts. So this has been found out using this volcanoplan. Similarly, if you want to generate carbon monoxide from carbon dioxide using electrocatalysts, when you're doing the pathway are over here, as you can see, the first step is generation of this carbon dioxide anion radical, which is basically the most energy intensive one. But then if you see these different pathways which are there, you look into the volcano plot, in this case you will find that it is gold, which is basically the best electrocatalyst if you are trying to generate carbon monoxide from carbon dioxide. Okay? This is the thing. So what is the essence of electrocatalyst design for carbon dioxide reduction? So for the production of formate or formic acid, tin, bismuth, palladium and lead-based materials can reach nearly 100% Faraday efficiency, but require high overpotentials and have low current densities. Whereas for carbon monoxide production, gold and silver-based materials remain the most active and selective catalyst. Single atom catalysts right now have been shown to have high catalytic activity, selectivity, and stability for catalytic reduction of carbon dioxide to carbon monoxide. For the production of highly reduced C1 and C2 plus products, copper-based materials provide the best catalyst. So if you really want to produce highly reduced carbon 1 or carbon 2 products, in that case, copper is the best catalyst. But still the best performing catalyst, whatever you have in the lab scale, it doesn't meet the requirement for industrial applications. So you have various catalyst design strategies, as I showed in the last slide. You can reduce the size to nanoscale level. You can expose specific facets. You can do quantum confinement, doping, alloying, and defect engineering. And these have all been developed to modify the electronic and geometric structure of the catalyst so that their performance in carbon dioxide reduction can be enhanced. However, so far, no design strategy has been reported to improve the carbon dioxide reduction performance to the level which is required for industrial application. Now coming to one of the last topics, which is photocatalytic water splitting. So this process, is basically you are splitting water to generate hydrogen and oxygen. And in this case, we are using a photocatalyst. So the delta E value in this case is 1.23 volts, delta G is 238 kilojoules per mole. So the step 1 in this case is going to be what? Photon with energy above 1.23 electron volt has to be absorbed by the photocatalyst material. Then photoexcited electrons and holes, they will separate and they will migrate to the surface. Then the adsorbed species, which is water, is reduced and oxidized by the electrons and holes respectively. So this is how the photocatalytic water splitting reactions occur. So the most important thing for a photocatalyst is this band gap. You need a band gap of the material which should be higher than 1.23 electron volts, but less than 3 electron volts, because what you need is the visible light, because solar light is mostly having visible light. The ultraviolet part is very less. If you're taking a high band gap material, then you can use only the ultraviolet light, and that is only 4% of the solar spectrum. So definitely the efficiency is going to decrease. Also, you need a material having very high crystallinity, because if it is low crystallinity, there are defects, and these defects will act as recombination sites. And so your electron and holes are not going to get separated enough for the photocatalytic process to take place. And of course, your material should have long-term stability, because then otherwise, what will happen is your photocatalyst is going to corrode. So if its application definitely is compromised. So the requirements for a photocatalyst to be viable on large scale usage involves high quantum yield, being inexpensive, earthly abundance, then it should be recyclable, it should be non-toxic, it should be resistant to corrosion and photostable, and it must also have a very long lifetime. So these are the points which you need to consider when you are designing a photocatalyst material. And you can see this different photocatalyst material where you have, the conduction band and the valence band and how this photocatalysts are arranged. So wide band gap semiconductors, which are like zirconium oxide, potassium tantalate, zinc sulfide, strontium titanate, titanium oxide, zinc oxide, and silicon carbide, they utilize only light in the ultraviolet region for photocatalytic reactions. And so they result in low solar to hydrogen conversion efficiency, and that is why they are not preferred that much. What you need is something for which basically the band gap is, not that great. So you can have this molybdenum sulfide, for example. You can have cadmium sulfide, you can have cadmium selenide, gallium phosphide. So these are, better materials compared to that. So now if you look into the periodic table, you will find that most of the metal oxides which act as good catalysts, they are kind of concentrated within the D0 system, which is, marked by the red, or the D10 group. So this D0 system, it acts as a very good electron acceptor, whereas the D10 group acts as a very good electron donor, and obviously that kind of facilitates the catalysis process. So that is why these kind of metal oxides are most applicable in case of photocatalysts. So what are the different development techniques? So what you need is basically you will have the photocatalytic material, but obviously as you saw over there in the valence band and conduction band, the way it is there. So you need to kind of play around with the level of the valence band and the conduction band. And how do you do that? By using doping techniques, by forming heterojunctions, by doing dye sensitization. You can do sensitization with noble metal loading. You can increase the photocatalytic active area by, changing the surface, that you can have a porous kind of material. Also, you can have something which is like hollow. A lot of pores can be generated. So that is how you can increase the area of the surface area of the material. You can modify the surface. You can have nanostructures. Obviously, the surface area increases manifold with nanostructure. Then you can modify with co-catalysts. So these are the different ways in which you can kind of do the photocatalyst development techniques. So with this, I think we have covered whatever is there for your catalysis materials. And in case of any questions, you can always write to me. And with this, we come to an end of the Advanced Materials Chemistry course lectures. And please go through all the lecture slides taught by all the different lecturers. And I think you have also been given all the activity sheets, assignment sheets have also been given. So please return them on time. And we will be having the exam sometime next month. And with that, very good evening to you. Have a great day.